Class has started, so I just want to go ahead and welcome everybody. So I just put a couple of questions down there that you should be thinking about. Um, have you done all of your homework? Make sure you're getting that done. I have some of you guys who have not done your homework, or some people who they asked for extensions and they're doing that. So make sure you guys get on top of that. Um, also, ooh, my hand just appeared out of nowhere. You guys, I haven't heard a lot from you. So in my office hours, I think I've had 3 pre-calc students and I have 2 pre-calc classes. So that's not super great. So make sure that you guys, if you have questions, that you either are emailing me or are asking them. Um, so please make sure you do that. I know some of you are emailing me and I appreciate it. I'll be getting back to you after class. Also, next class will be our last class on review, chapter 1. So let's make sure that you guys are feeling good about this chapter in the review. So next class, I think we're doing inverse functions and tidying that up, okay? So hope everybody's doing okay. Hope you guys are having a good day. We got 2 things that we're going to be learning about today. We're going to be learning about parent functions and transformations. So let's get started. Let's just dive right into it, right? Because who just wants to sit here and look at their teacher in the tiny little corner up there, right? It's a little weird. That's not what you guys signed up for. So 1.6, we're going to be looking at family functions. And family functions just means that they're types of functions, right? So when we do family functions, we look at the parent function. Okay, and if you don't know what a parent function is, a parent function just means no transformations. Okay, and so what I mean, so it's important, and this is the expectation moving forward, is you guys have to have these memorized. You got to know them because if you don't know them, you won't know where there's problems, where there's holes, where there's issues. So I know that's kind of like, ugh, but yeah, you need to know them. And if you're going to be successful in calculus, you can't be slowed down by having to look up parent functions. You're going to be expected to just know them. Okay. So what I mean by, so that's what a parent function is. It's just a family function that with no transformations. Remember transformations, right, are your and we're going to go over this in 1.7, your translations, your reflections, your dilations, and that. So no transformations, okay? Now, to do this, I could just draw all these pictures and go over them, but what I did instead is, since this is review, I have posted on Google Documents, and I want to watch this. It's going to transition to a different screen. That didn't work. There we go. Okay, cool. So what I wanted to show you was in Google Classroom. So this is our Google Classroom. Make sure that you guys go to the classwork tab because that's where everything is going to be. Okay. And then if you scroll down to resources, I added something to the resources, right? And also just a reminder too, the links to classes I've been posting, here I can just pop this open. I've been posting all of our class videos, so if something happens where you disconnect or you need to review stuff, you can go back here and see our videos, okay? No, what I wanted to look at today was review of parent functions. So if you click this, a PDF will open up, and it's the most amazing resource that I could find for you guys to know of the graphs of parent functions. So we're just going to go through these one by one, and if I'm going through something and I don't explain it well, you can go ahead and just put a comment in the chat box, okay? So the first one we're going to do, let's see if I can get this going here. We're going, yeah, okay. So the first thing we're going to do, I need to zoom in here on my little application, because there we go. Zoomed in too much. Okay, so the first thing we're going to do is take a look at linear functions. Okay, so linear functions, you should be pretty used to this. So it gives you a sloped intercept form. But remember, we have point slope form. That's going to be a little bit more helpful. So how can I add text here? I want to add text. I don't know how to add text. So the more helpful one is y1 equals m times x minus x1. Sorry, this is the only way I know how to add text. So there we go. So make sure that you guys know this equation for linear functions. That's the most important one, right? So it's y minus y1 equals m times x minus x1. So that is the point slope form. So you want to make sure to know that and have your notes, okay? All right. So, so linear functions, okay, know the equation. So things that you need to know about linear functions, there is no input that doesn't work for linear functions. So this is really interesting. Do you guys see my mouse over the domain right now? Okay. All right. All right. All right. So the domain right here. So make sure that you guys know that everything works for the inputs. Okay. For the range, except just the only occasion where the range has an issue is when the slope is 0, right? Because that would be a horizontal line, right? So I can just draw that really quickly, right? If you have a horizontal line, m equals 0, right? Then the range is only going to be that output for what that line is, right? So if this is 4, oof, come on, you can do it, yay! So that means that the output here would only be 4, okay? Another thing, so the intercept, we know the y-intercept is being b, right, and mx plus b, and you have to know that if the slope is positive, you're always increasing, and if the slope is negative, you're always decreasing. The negative b minus m, they just take this equation and they solve for x when y is 0. So you can imagine they subtract b from both sides and then divide by m. No one has said anything in chat, so I'm just going to assume that everything I'm doing right now is working and it's showing up on your screen. Okay? All right, absolute value function, you have to know it absolutely. All right, so just remember with an absolute value function actually isn't a function, it's a piecewise, right? And a piecewise can be a function, but we'll get into that later. So one thing that we need to remember, right, it's actually two lines. It's y equals x and y equals negative x, right? So again, things that you have to remember about this is the domain, anything works, nothing breaks. The range, notice how we use a bracket here because the lowest it can be is 0, and they put a little dot there so you can tell that it equals, okay? When it says intercept, that just means the x and the y intercept are the same. So that's what this means. So see how this one says x and y intercept, this one just says intercept. You have to know when it's decreasing. You have to know when it's increasing. Notice how at 0 here, it's a parenthesis, not a bracket, because at 0, it's neither increasing or decreasing. Okay, but we don't say it's constant either. It's kind of weird because I just kind of supposed to do this magical finger thing and tell you that, oh, I guess you can't see my camera here. Oh, nope, that's not what I wanted to do. That's not what I wanted to do. Okay, this is what I wanted to do. There I am. Pretty cool, huh? All right, so I had to do that just because I wanted to show you the magic fingers. Okay, so we'll talk about, you'll talk about what that point is in calculus, okay? It is an even function, which means it has symmetry. So to know for sure, brackets means that it's at least or most it can be. So I think you're hitting at the right terms. So it means that it can equal. So I like it to an inequality. So if I draw this, a bracket, so here's a bracket, there's a bracket, oops, is the same as like this. Right, so it can equal it. So in interval notation, you always put the lowest, right? So it's the low. Oh my gosh, I should stick to. So that's in W, and then you have your high. And so here, this is just saying that it can equal the low, but with the parenthesis, you can't equal the high. Man, this whiteboard function is not super great. So I hope that answered your question. Okay, so a bracket just means it can equal. That's it. It's not an inequality, so it's not going to have the words least in it. So it's just, it can equal. Think of it, it's more of like an open circle. That's better. So if I had an open circle on a graph, that is a parenthesis. If I had a closed circle on a graph, that is a bracket. And I know you guys are super impressed with my drawing skills, right? My first grade teacher said that I was the best in the class, so. Okay, so closed circle, I have brackets, and then open circle, I have parentheses. All right. So you need to know absolute value function. What else do we have here? We have square root function, okay, or a radical function. Square root you need to know. So a square root of 0 works, so it's important that you include 0, 0. And then it's like the claw. So if you took your finger like this, it's like the claw. I always call it the claw function. Okay. Make sure here, so domain, it can equal 0. Some people sometimes forget that you can take the square root of 0 at 0. The range, it can equal 0. The intercepts are the same. It's increasing from 0 to infinity. Okay, again, these are the parent functions. We're going to take a look at that. So greatest integer function, you don't need to know it. Okay, so we can cross this out. Okay, don't need to know that. Not important, not going to be going from there. You do need to know quadratics, okay? You need to know domain and range, okay? So it's important, right? So what this is just saying, so A is the leading coefficient, right? If it's positive, you're smiling. Do you guys remember that? Positive quadratic is smiling. A negative quadratic is frowning, right? So that's going to change your range. The intercept's always going to be 0, 0. And then got to remember we read left to right, right? So it's decreasing if it's positive, if it's happy, and then increasing. If it's sad, then it's increasing and then decreasing. So always remember to read left to right. It's an even function, which just means it has y-axis symmetry, and it has either a minimum or a maximum. Cubic functions, you need to know cubic functions. I think at this point, I just need to tell you what you need to know and not to know. So everything on this first page except greatest integer functions. If I go down, you need to know rational functions. You need to know exponential functions. We're not going to do logs now, but you do need to know logs eventually. So, but we're not doing logs right now. We're going to spend time on logs another time, okay? And then in the future, we're going to be doing sine, cosine, and tangent. And then in the even more future, we're going to be doing the reciprocal of those as well, okay? And the inverses, okay? So for right now, what you need to know, because this is going to be on our midterm, is linear, absolute, square, root, quadratic, cubic, rational, exponential, and you should be looking at log, okay? So that's it for 1.6. Does anybody have questions? Oh, that's not it for 1.6. One thing I want to add in here is how to graph piecewise functions. Okay, so I have a piecewise function I want to graph for you. So this is going to be f of x equals, and then we're going to go 3 square root of x squared plus 10 if x is less than -1. And then we're going to have 2 times the absolute value of x minus 5 if -1 is less than or equal to x is greater than or less than 1. And then 4 minus x minus 2 squared if x is greater than or equal to 1. All right, so this is a doozy, but this might show up on a midterm because, or a homework assignment, because you're graphing all the parent functions, okay? So how do we go about doing this? Well, especially if you're just sketching. Okay. The first thing you're going to do is these points right here. These are your important points, right? And we're just going to start here and take a look at this. So if it's less than -1, right? So here's -1. If it's less than -1, I'm going to have 3 times square root of x plus 10. So I might just look at this and think about, okay, well, I know the parent function for this is the square root. So I'll be like, okay, I know that the parent function starts at 0, 0. So obviously there's a transformation here, right? So remember, and we're going to talk about this in a second, if it's inside the function, it's changing the input. And remember, the input on a graph goes left to right. And so inside is backwards. So if it says plus 10, I'm really subtracting 10. So I'm going to go 2, 3, 4, 5, 6, 7, 8, 9, 10. So I know it's going to start there. Okay. And then it's the square root. So I'm just trying to think. Let's take a number that we know how to take the square root of. How about 25? So no, let's do something smaller. Let's do 9. So negative 1 plus 10, right, would be 9. The square root of 9 is 3. 3 times 3 is 9. All right, so so this point right here is -1, 9, and then I know it's the claw, so it's going to look something like this. Oops, that didn't have a lot of curve on it, did it? There we go. I'll just make that line real thick. Okay, so not the greatest of line, right? And it should really just go like that. I'm a little disappointed in my line. Okay, we make it thick enough no one can tell. All right, so you have the square root function. Sorry, mine doesn't look super like a square root. So that's all I did. I looked at some key points, right, to sketch it. So I know the parent function starts at 0. I figured out where that is. And then I have this interesting point at -1. I could have found more points, but I don't have the time. All right, this next one. So if we look at this one, all the transformations are on the outside, right? So remember, transformations on the outside, they're normal. So this is shifted down 5. So I'm going to go down 2, 3, 4, 5, okay? And then I know I have a point here, right? And then, one thing I didn't do you see right here how it says it's less than -1? It can't equal -1. So I'm going to put a bad open circle here. Okay, because it doesn't equal here. So here, though, if I plug in -1, so the absolute value of -1 is 1 times 2 is 2, and 2 minus 5 is -3. I can put a big solid dot here, okay? And in calculus, we call this a jump discontinuity because you have to jump to get from here to here. Okay? And then it looks like I go to 1, so if I do a 1 over here, I can plug a 1 in, and 1 is 2, and 2 minus 5 is 3. So I get -3 here. Oop, and then I made a mistake again. This should be an open circle, because again, it can't equal. So again, we're taking a look at these. So this should be an open circle because it can't equal 1. And then I have a quadratic. So with a quadratic, a couple things I need to notice, right? This in the inside is going to move it right 2, but then the negative over here, that's going to make this a sad quadratic. So it's going to be frowning. It's going to be opening down. And then this 4 is on the outside, so it's going to shift it up 4. So let's take a look. So it shifted to the right 2 and up 4, but let's just plug in at 1 and see what it looks like. So if I plug in a 1 minus 2 is -1. So -1 squared is +1, times this is a -1. So 4 minus 1 is 3. So at 1, I'm at 1, 2, 3, and it is an equal. So it might be good to know where my origin is. So I said that it shifted over 2. right? So if I plug in 2 here, that's 0. 4 minus 0 is 0. So then goes up here, and then it's going to go down. If I was really short on, I mean, if I had more time, I could find the x-intercept, which is not too hard here. I just set this equal to 0 and go from there. So do you guys see how I sketched this function using a piecewise? Again, the key here is using all of the important points that it gives you, and then knowing the parent function, so important, right? So for the square root, it's like we know it has to be 0 at some point. For the absolute value, we know there's a vertex point. And then for the quadratic, we know there's going to be a vertex point. Okay. Does anybody have questions about that? So I actually graphed this in Wolfram Alpha, and I wanted to show you a better image of this. Let's see if we can do this. So that's actually, so I mean, I'm not too bad. Do you see how the square root, it starts, you know, a little steeper than it, and it slows down. So that's not too bad, right? Yeah, yeah, yeah. All right, okay, cool. So yeah, that's pretty close to that. Okay, okay. I hope you guys are doing okay. You guys aren't really giving me anything to work with, so I'm kind of just doing my thing. All right. Okay, so 1.7. Very fun, yes. Reminds me of the snake from Jungle Book. All right, so 1.7. Transformation. I guess if you guys wanted to summarize 1.6, 1.6 is that document that I shared with you. You need to know it, and the reason why you need to know it is because when I was graphing these, right, I used my understanding of parent functions to be able to graph it. Like I knew that this one started at 0 and curved up. I knew that this one, right, is a V and had a vertex and went like this. And then I knew this one is a sad face because I knew the transformation. So make sure you guys know the parent functions. All right. Transformations, all right? Transformers, more than meets the eye. Autobots, roll out. Come on, you guys, I mean, the movies ruined it, so your generation kind of had transformations ruined, but the comic books were super bomb. And the cartoon TV show was pretty good too. All right, so what do we got? We got translations, right? And these aren't the kind of translations where I'm going between languages, right? This is when we shift an image up, down, left, right. Okay. So I'm not sure how to focus on this. There we go. So we're going to shift an image up, down, left, right. You guys were hoping that the autofocus would help, you know, improve my penmanship. Ha! There you go. G.I. Joe is not better, and I will fight you to the death over that. All right. So things you just need to know. So inside. Okay. Inside the function. Okay. So when I say the function, I'm talking about the parent function, right? That's the input. Oh my gosh, you see what I did there? Inside, input, inside, input, inside, input, in, right? So the inside is the input. It is the x-axis. Okay? Okay, this is, if it's inside, it's backwards. Okay, it's always backwards. So for example, right, if I have x minus 2 squared, it says left 2, doesn't it? But it's backwards. So it's right 2. If I have, what's another function? If I have the absolute value of x plus 3. See, it says to the right 3, but that really means left 3. Okay? So just remember, if it's inside the function, it's backwards. And that's true with dilations too. So we're going to get to that in a little second. Okay? If it's outside the function, okay, if it's outside the function, then that is the output. Outside output, right? And that means that's the y-axis. Okay? So again, it is normal. Goodbye. All right, so it is normal. So here's some examples of this. Okay, we're gonna have, just really quickly, if I had x squared plus 2, that's just up 2. Okay, or if I had the absolute value of x minus 3, that is down 3. Okay, so inside is backwards and outside is up. Nope, so just remember, if it's outside the function, so the function is squared, right? You can think of it like this with parentheses. If it's outside the function, it's output, so it would be up. Okay? Oh yeah, this is right. Is that what you're referring to? My inability? Yeah, you like RIGH? It's shorthand for right. I get it if you guys don't, have the cool lingo because you aren't as cool and hip as I am. But Rye is the new right, so, I get it. You guys will catch up with me, and I appreciate that. And Brandon, I appreciate you calling me out. I definitely dropped the T, didn't I? All right. All right, so that's dilations. That's translations. That's it. If you guys don't have any questions, then that's fine. Okay. We're doing great for time. So next up, let's talk about dilations. So dilations always give people an issue. So dilations is when we multiply. So we make bigger or small. Make bigger or smaller, so scale factor, right? So if our scale factor is greater than 0, we get bigger. If our scale factor is less than 0, we get smaller. If your scale factor equals 1, you're just making a copy and it's not interesting, so we don't talk about it. And if you end up being someone who's a copy person, I'm sorry. But actually, oh my gosh, side story. Scale factor of 1 is actually super hard to happen. And if any of you have ever worked in engineering or architecture, if you make something that is a one-to-one diagram, copying that is actually really difficult because most copy machines or printers don't do a one-to-one. So actually, this is really difficult, but not the scope of our class. Okay. So dilations, there's going to be vertical dilations. Okay, so this is output. So everything is normal. And the reasons why everything is normal is because it happens after the function, right? So remember, if I have a function, oops, I meant to do parentheses, but not there. I just saw the x. So if I have, for example, x squared or 2x squared, sometimes it's helpful to go like this and put parentheses. The little 2 up here is the function, right? And so the parentheses help us do that. Do you see how the 2 is outside of the function, right? So order of operations, I do parentheses first. So everything is normal because it happens after the function. Okay, so the function doesn't mess with it. So this right here is a vertical stretch. And all you're doing is you're taking all of the outputs and multiplying by 2. So you might think of it as all outputs are doubled. Another example would be oh my gosh, I just thought of a really good example, but it's not what I wanted to do. Let's say 1/4 absolute value of x. Okay, so this is a vertical shrink. All outputs All right, so that's vertical dilations. If you had questions, I'm sure you guys would tell me. You guys seem to only ask questions when I make mistakes, so maybe I should make more mistakes. Right? Huh? I'm on to you guys. Okay, so let's do horizontal dilations. I always worry too when you guys aren't responding that my internet just goes out and no one's actually there. So horizontal dilations, how am I doing for time? Holy moly, 50 minutes is fast. So horizontal dilations, so just remember it's the input. So everything is backwards. Okay, because when I say backwards, you have to remember the opposite. I'm using inverse operations. So when I say backwards, I really am meaning inverse operations, right? So what's the inverse operation of add, subtract? Of course they will, Bethany. I am the YouTube streaming champion. Yeah, they'll be up on YouTube. Remember, in Google Classroom, I have a document with all the links. Okay. And if you have questions, yay! If you have questions, you can just ask. Okay. So when I mean inverse operations, right? So when I did input before, right? So the opposite inverse operation of subtraction is positive, so it goes to the right too. So this is important because for examples of horizontal dilations, okay, you see how the 2 is inside the function, right? So the parentheses are super important, right? So it's inside the function. So this, we have to remember, this is multiplication. This is 2 times x. So what's the inverse operation of 2? I mean, of multiply? It's divide. So this is really dilated by a factor of 1/2. Okay. All right. Okay, and what this means, and some people get confused by this, is this, so if it's dilated by it, so that means that if it was out like this, that you're pushing it together like an accordion, and that's confusing to people because when I say it's dilated 1/2 horizontally and I'm smushing it together, doesn't that mean that things happen faster, right? You get to those higher so you can also think it's dilated by a factor of 1/2, but you can also think of it as you're getting to your high, like so for example, if I look at this, right? So if this was x squared, then 2x quantity squared would be steeper, like that. Okay. And so you can think what we're doing, and you can see here, we're pushing this in, right? We're pushing that in, and that's what that horizontal in. Another thing that you can do here is you can pull out the 2x. So what's 2 squared? 2 squared is 4. So this is also the same as 4x squared. So a horizontal dilation factor of 1/2 is the same as a vertical dilation of 4. Okay, so that's why it's confusing with dilations, is that not all functions have this, right? When we get to trigonometry, you're not going to be able to do this. But for some of these family functions, there's an equivalent vertical and horizontal as well. Okay. And then most importantly, I want to do one that tricks a lot of people. And that is, let's do a square root. We haven't done a square root. When we have this. And the problem here is when the leading coefficient sorry, I'm just going to call it coffee. The leading coefficient is not 1. Okay? And when you have that, then you have to factor it out. Okay, and I'm talking about that guy right there. Okay, so and the reason is where the 1/2 came from, it's backwards. So we don't say, so this is the graph of the 2x squared, right? So it gets skinnier, like it's going up skinnier. Whereas this one's wider, okay? And the idea is, if you were to think of this normally, you would think like, oh, twice, I'm like pulling this out. So it's gonna get, so instead of looking like this, it's gonna go, but instead, what we're doing when you're multiplying like that, you're pushing in on it and it's going up like that. Because, and this is what I was trying to show here, a dilation factor of 1/2, when you're pushing it in, it's the same as having a vertical dilation of 4. And you can think of a vertical dilation of 4, it's going to make it a lot skinnier, right? So just like here, right, if it's inside, it's backwards, right? So the opposite of -2 is +2. So the opposite of multiplication is division, right? So you're doing backwards. So that's where that's coming from. Okay, so that's where there's the 1/2, because this is 2 times and this is divide by 2. So they're opposites. They're inverse operations. Okay. Now, if you don't like that, you can always remember you can pull it out, and then now you just have a vertical dilation of 4. We're not doing inverses until next class. So you're using the word inverse rock. So how do I know to use an inverse operation? So if it's insides, anytime it's inside the function, you're always doing the opposite of what it says. You're always doing the inverse operation. That's it. Okay? How am I doing this? So yeah, so whenever it's input, so notice here horizontal, it's input, so everything is backwards. And then here, if it's inside the function, it's always backwards. Okay, so if it's inside the function, it's always backwards. Okay, and then the idea here is, think of an accordion, right? So I'm going vroom, 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 vroom. Okay, so horizontal dilation, right? That's in the x direction. So I have a horizontal like this. Okay, so what I'm doing here is that 2 in there is I'm compressing it by a factor of 2. Okay, so if this was my accordion, I'm compressing it by a factor of 2. So I say it's 1/2 the width of the original. Right? See how that's confusing? So I'm compressing by a factor of 2, which is like 1/2 the original length, right? So compressing by a factor of 2, 1/2 the original length. You can also think of it as, I had this, and then I'm just taking my outputs and multiplying it by 4, and it gets the same effect. So this is just 2 ways of looking at the same thing. These are the same function. Okay. I know that's confusing. I'm trying to spend some time on it. Okay, so why do we have to factor out the leading coefficient if it's not 1? Because this coefficient affects the translation. So if you were to look at this and you were to say, oh, look, this is it's shifted to the right 2, you would be wrong, because this isn't 1. So what we're going to do is we're going to factor out the -1. So when I do that, this becomes x is positive and this 2 is positive. Do you see how now that changes what we're doing? Okay. And when you have a horizontal dilation that's negative, we have 2 things here. So it's left 2, and it's reflected over the y-axis. Okay, but if you had done this here, you would have gotten the reflection right, but you would have gotten the translation wrong. So if your coefficient is not 1, make sure that you guys are factoring out that coefficient, okay? And we'll have an example problem of that in just a second. Okay, so I agree. Horizontal dilations, for some reason, they mess people up, and I think it's just because it's backwards, but then they're like, wait, what does this 1/2 mean, right? Because it's confusing, because it's flipped. But just remember, it's like an accordion, and it's half the length it was before, right? So everything is pinched in half that distance, okay? You can think of that as that. Hey, thanks, I appreciate that. 10 minutes. we're going to get cooking here. All right, so just a quick thing on reflections. Okay, so reflections, there's two reflections that you need to worry about. So that's over the y-axis. Okay, and that happens when you have a negative with the input. Okay, and then over the x-axis is when you have a negative on the outside. Okay, quick example of this, if I have negative, oh no, that's a terrible one because that has symmetry. So if I have the square root of negative x, okay, that would look like this. Nope, that's also a bad example. Geez, people. How about this? So I want to make sure I get this right. Okay. All right. So again, this is negative x cubed, and x cubed would normally look like this. Okay, so it's reflected over the y-axis. Okay, reflection over the x-axis. Now this is one that I can do a little bit more better. So that would be negative x squared. So then I would have, this is x squared, and then I have negative x squared. Okay. So again, negative on the outside flips it over the x-axis, negative on the inside flips it over there. Okay, just make sure you might have to factor. So I'm writing, check to see if factoring is needed. Okay. All right, the last thing I want to do, and I don't think I'm going to run out of time because I'm pretty good at what I do, if I say so myself, is I want to look at multiple transformations. And then you guys are really good at reminding me. I just want to really quickly talk about how to write an equation based off a transformation graph. Okay. All right, cool. So let's try this out. So I have an example. G of x equals 2 times the square root of negative x plus 3 plus 1. Okay. So when you look at a problem like this, I always identify what's the family function, right? So the family function here is square root of the square root, okay? So then it's really important, if you're having troubles with this, write parentheses, right? There's my inside, here's my outside. So sometimes it's easiest to do the outside first. So for example, I have a vertical dilation of 2. Okay, I have a vertical translation of up 1. Okay, so those are the easiest because they're just normal. Now on the inside, notice, boom, right here, we got to factor that. Okay, so I'm going to go over here to do my work. So to factor that, right, I'm going to have, I'm going to pull out the negative. I'm going to have positive x minus 3. Okay, so really I have a horizontal translation right 2 or right 3. Put the T on it this time, Brandon. And then I have a, so this is a reflection. So I'm going to have a reflection over the y-axis. Okay, and we should be able to sketch this. So I know that normally, right, that's the square root, that's my parent function. So what am I doing? I'm going up 1. I'm reflecting over the x-axis. And then aren't I going right 3? So, okay, so I'm starting here. and then I have a factor of 2. So think of a square root that we normally do. What's the square root we normally do? Square root of 4. So if I go over 4, so that should be 2, but it's times 2, right? So it would normally be at 2, so now it's going to be at 4. So it's going to look something like that. That's the bonus of function notation. You don't have to write it twice. Okay, and gosh, I'm doing great for time. Maybe I went a little too fast there. So with multiple transformations, just make sure you can identify all of the transformations. Make sure that given a function, you can sketch a graph, right? So you should be able to be given any family function and sketch a graph just based off of functions. Okay, and then if you're given a graph, you should be able to write the equation. Now, to do that, have you ever heard your teacher say guess and check is bad? Have you guys ever heard that? Yeah. Guess and check is great. I mean, it's slow. So if there's a better way of doing it. Now I say that, and if you go to calculus and you guess and check, you're going to be in a bad place. But sometimes guess and check is good. I'm not going to do a real example. I'm sorry. I'm just going to make one up. So here, let's do this. So I'm going to do a really easy one. Oh my God. I'm thinking too hard, so I go. Okay, so I'm going to write the equation. And so let's see here. This is negative 3, 4. This is negative 1, 2. And this is negative 5. All right. So the first thing you want to do is you want to identify the family function, right? So the family function here is a quadratic. The next thing we want to do is we want to figure out the vertex, right? So we're going to get to our vertex from our translations. So if I look at my core function, okay, how did I get there? So let's see. It looks like I went left 3, so I'm inside the function, so I'm going to work backwards. It looks like I'm up 4, I'm outside the function, so I'm going to work normally. Now, notice how I'm sad, so I'm opening down. So whatever number out here is, it's going to be negative, but let's check that out. So normally, if I go over 2, so if I go over 2, that's 2 squared, right? So 2 squared is 4. So I would expect if I go over 2 from my vertex, I would go down 4, but I don't. I only go down 2. So if I only go down 2, isn't that half what I would normally do? So I could go 1/2 like this, and boom, there's where I go. Now, for extra points, you could try to put this in and write the equation with the horizontal dilation. In this case, it would be 1/4. But I digress. That should be enough to get you there. Your homework is posted. It should be posted shortly because it's on the timer and the timer is a little delayed. If you guys have questions, please let me know. Check out the document on parent functions in Google Classroom. You need to know those. And then transformations, if you guys need help, let me know. In the last few seconds of class, does anybody have any questions or comments about what we're doing? Again, so what I meant here, it's okay to guess and check. Yeah, go ahead and ask your question. So it's okay to guess and check, right? So like here, I can just plug in the points. So I can try -1, and it should equal 2, right? So do you see how you can guess and check? just take a point that you see on the picture and just plug it in and see if it works, and if it doesn't, adjust. Okay? Any wise words for all those heartbroken people? Oh, yeah. So what I would say to that is most of you guys are what, 17, 18, 16? So I would say the average life expectancy is what, up to 90, 95. So 15, 14, yeah. I got a wide range of students in here. So for those who are heartbroken, I would just remind you that you haven't even lived a quarter of your life expectancy yet, and that that there's a lot more to going on, and definitely there, I can't deny that that sometimes life is difficult, and it's gonna break your heart, and it's gonna feel like your heart will never heal. But I can tell you that that your heart will heal, and that there's lots of things in life to love, and there's lots of things in life to be loved by, and that time will bring and heal, and time will bring new loves, both things to love and both things to love you. So yeah, I hope that's wise words. But I just want you to know, when I say time heals, it's not like that time is fun. It sucks. But I think that's part of growing up, is learning how to deal with emotions, learning how to deal with heartbreak, learning how to deal with all of that. Anyways, hey, class is over. I really appreciate that. Hey, I love you guys. And if there's anything I can do to help you, just remember to like and subscribe. No, that's a joke. Remember, if you have questions, email me. I love you guys. I want you to do well. I want you to feel good. Math is only fun when you get it. So I want to make sure you guys are getting it. So if you have questions, come see me, my office hours. And I love you guys. Take care. Stay away from the smoke and COVID. Okay? I do. I think we should all be friends. Bye, guys. If you have questions, you can stay on, and